Thank you very much, and thank you very much for the invitations. This is a little weird because I hear myself, but we'll try to work through this. So I'm going to start by trying to explain the different parts of the title here. So I'll start with trying to tell you what is the Caffarelli-Kohn-Nirenberg inequality, that I'll write it as CKN, not to write it every single time. So the classical Caffarelli-Kohn-Nirenberg inequality is this inequality here. It's kind of weird not to have a pointer either. But this is for dimensions n bigger than 3. And somehow what you need here, I'm going to assume that intentionally I put W to be in a very regular. Of course, you can extend by density here to larger space. But today, I'm just going to assume that W is compactly supported and smooth because I'll be changing the parameters. And this is saying that W also has to be in some sort of weighted Holder space according to those weights. When alpha is equal to 0 and beta is equal to 0, this is an inequality that's very well known. This is just the okay, so let me maybe go back to that later. But this is it's a Sobolev inequality. But here we want to explore a larger range of parameters. And something that I was coming there, that I wrote the inequality for n bigger than 3, because in the case n equal 2, you still have an inequality, but your range of parameters is slightly different. Okay, so what I was saying. So when alpha and beta is 0, it's just the classical Sobolev inequality, and maybe a bit less known is the Hardy inequality in the case beta is equal to alpha plus 1. That's a particular case of this inequality. So some people say that this is sort of an interpolation inequality. That's a way to understand this here. Okay, so it's more or less well known to everyone that the Sobolev inequality in general is not attained, not in null Rn. But here we're interested in studying exactly the range of parameters that is not that is when the inequality is attained. And in that case, the solutions that attain equality, I will call them extremal solutions. And they solve an equation that I'm not going to use right now, but I'm going to write it later. For now, I just say that these are solutions to certain equations. And something that is going to be relevant in a minute is that all extremals are solutions to the equation, but not all solutions to the equation are necessarily extremals of this inequality. Okay, so, well, I already said that they do not always exist, but sometimes they do. And if you look at the inequality that I had before, it's very natural to think that maybe this extremal solution should be radially symmetric, because everything is very radially symmetric in this equation. And the answer to that actually is that this is not always the case, that sometimes you have extremals that are radially symmetric, but sometimes they're not. And what we want to discuss a little bit today is sort of that breaking of symmetry that may happen. And you may even have, there are two things that maybe is important to mention here, that you may even have in certain situations that you have an extremal that's not radially symmetric and one that it is radially symmetric. So they're not unique either, always. Sometimes they are, sometimes they're not. And sometimes you may have solutions that are radially symmetric, but they're not extremals. Okay, so all these things can happen. In this classical case, this has been studied for a very long time, so this is quite well understood by now after many, many years of working on this. And this is a picture of that paper where they show how is the symmetry region and the symmetry breaking region. So the darker gray that you see there is where the solutions are not symmetric. The lighter gray is where they are symmetric, and that line in between is where you have both situations. So you have sometimes that you have a symmetric and a non-symmetric at the same time. And it's a curve. I mean, they can show that this is a curve. Okay, so in the title, I had additionally the word fractional, and this refers to, as I said before, my W in some sense is in a weighted H1 space. So that 1, I want to change it for another parameter that was going to be less than 1, an HS. And in that case, inequality, you also have something. You can also change it for something that is bigger than 1, but today I'm going to change it for something that's smaller than 1. And the inequality that you get in that case, it looks like this. So this is some sort of weighted Sobolev fractional norm, in the sense that you don't have the derivative, but you have something a little bit weaker than the derivative. And your range of parameters here, again, changes. As you see in the first case, when n was bigger than 3, I didn't have restrictions on alpha, except that it couldn't be equal to that quantity, to n minus 2 over 2. Now I have a restricted range, more like in the case n equal to 2. Although I have to say that in this case, I don't know if this is optimal. I mean, many people have studied this, and this is the cases where it has been proved, but I'm not sure actually that it's not true in other cases as well. And again, like the case n equal to 1, you can also study, and you are going to require here that the gamma is something between 0 and 1/2. This is going to be the additional restriction in that case. And in the title, there was also word limiting. And by limiting, what we want to see is what happens with the solutions when the parameters approach the region where the inequality doesn't hold. That's the limiting in this case. So let me, okay, so here I have a little bit of a few facts in the fractional case that, again, we have some sort of different equation that I'm going to show you later. Solutions, again, may exist or may not exist depending on the choices of parameters. And again, we have examples where they can be symmetric and where they can be not symmetric. But in this case, it's not so well described as in the other one. We know we have all these things, but we don't know the optimal regions as in the other case. So that's going to be relevant in a minute. So let me talk now about the limiting case. So in the case n equal to 2, the limiting case, I will refer to the case n is equal to 2. And this was, there was a paper by Esteban, Dolbo Esteban, and actually Tarantello. This is a wrong paper. It's another paper where they tried to connect the Caffarelli-Kohn-Nirenberg inequality and the breaking of symmetry with the fact that the Laplacian is a conformal operator in dimension 2. Okay, and they connect, and I'm going to explain this in more detail in a minute, that inequality over there that is called the Onofre inequality with the inequality that I showed you before. This is an inequality that has been used to show existence or non-existence of certain prescribed Gaussian curvature metrics. Okay, this poses abstraction of what kind of curvature you can prescribe on the sphere. Okay, so one thing that is going to be relevant is that in their case, they know explicitly certain radially symmetric solutions, and they know regions in which these were extremos and regions where these were not extremos. So somehow they want to use the fact that they know explicitly the solution to study the phenomenon of symmetry breaking. Okay, and I'm going to describe a little bit their proof later because we're going to do something similar in the fractional case. But for now, let me tell you that somehow knowing these solutions, they can show that if you have the Caffarelli-Kohn-Nirenberg inequality in dimension 2, then this inequality holds. Basically, they can recover this inequality from the other inequality. I'm going to describe that in a little bit more detail later, and then they do more things. In their case, everything that I'm going to tell you today is somehow simpler because they know explicitly the solutions, and I'm not going to know explicitly what my equivalent thing is going to be. So what this tells you is when you prescribe Gaussian curvature on the sphere, this helps you understanding what kind of abstractions you have. Not everything can be realized. And this inequality has been used exactly for that, to pose some abstractions that you need to impose when you're trying to find solutions to the Gauss curvature equation, so a metric that has that prescribed Gaussian curvature. Yeah. And then, exactly. So in some sense, in their paper, they want to see a connection. I haven't read the paper with all details, so I'm going to lie if I say exactly what they show. But somehow they want to use that connection to show why you have symmetry breaking. They want to give an explanation why there are regions where you have symmetry breaking in this case. And they go basically from one side to the other. OK, so let me tell you what's going to be the limiting case in our situation. Now I'm going to be in dimension 1. The parameter gamma is going to be converging to one half from the left side because that's a restriction that I had. and the other parameters are going to be converging to 0. Here is going to be important, and that's I'm going to keep it, that the way they converge, they have to satisfy this. The p epsilon was something that I defined when I wrote the inequality. That is important if you want to do computations, but for now you can think about it as a parameter. No, that was too much. Here. So this is the p, and the p epsilon is given by beta, alpha, and gamma, basically. So I'm gonna write it, but basically what we're gonna have is that this is converging to 0, this is converging to 0, so p is gonna be going to infinity, and the other things are gonna be going to 0, and we want to have some balance on how that happens. And this maybe I'm gonna keep, because I'm gonna keep referring to that. Okay, so let me write here that maybe that gamma epsilon converging to 1/2 from the left, that beta and alpha are gonna be converging to 0. That's more precise, but it doesn't matter too much for me. Epsilon, p epsilon is going to be convergent. This doesn't matter too much what it is, just that it's a positive number. And this is going to be converging to some b that has to be between 0 and 1. In the case of the previous paper that I mentioned, they give very explicit choices for this because they know exactly where the symmetry region is. So basically, my second line there, that we are on the symmetric region, we don't know exactly. We know some choices that would make that, but we don't know the best choice for that, let's say. So we know that this exists, but I don't know we don't know every choice that would make this to be true. The first statement in the theorem is that in that case, if you normalize properly, I'm also going to describe that normalization in a minute, then the functions converge locally uniformly, which is something that you don't need in the classical case because this is explicit, so you know exactly how they converge and what they converge to. So the second part is that the limit is something that is going to be a solution to that equation. That constant over there, that Said, I think, 1/2 is a constant that for now you can ignore. It's just a normalization constant. You wrote that the solution should be radially symmetric. By this, you just mean even. Even, yeah, because in one, yes. Is it true that in one dimension you can have a non-even meaning? Yes. In what? Yes. Okay. Yes. It's a discrete symmetry, no? Yeah. Yeah, but you still can have something that is not even, yeah. Yeah, but it's true. Here is even or not even, yeah. Yeah, so I was saying that then the limiting function is something that is going to solve this equation, and the inequality that we get instead of the no-free inequality is this inequality here. So here the eta plays a role because the measure is given by the eta, and yeah, so this is it. So let me see. I always go too fast when I have slides. So let's see. Let me give a couple of comments here. Okay, the inequality was known before. This has a name and everything. It has been used in the past to prove a conjecture before. I don't know exactly what role plays in the proof, but this was a known inequality. And the inequality that I wrote before was an inequality on S2. You can write this as inequality on S1 if you want to make the analogy closer. There are objects that I didn't define, like this 1/2 Laplacian. The 1/2 Laplacian corresponds to the Dirichlet-to-Neumann map. So basically, if you on upper half space, so if you prescribe eta here, and take the harmonic extension. So you take some u that is harmonic, and at the boundary is equal to eta. So let me call y equal to 0. Let me call this variable y. Then the half Laplacian actually corresponds to, of eta, corresponds to the normal derivative of u. The normal derivative of u at y equal to 0 with a minus sign, actually. But, that's what I mean by the Dirichlet-to-Neumann map. I will give another expression for this also in a few minutes. And here is what I said before. We know choices of parameters that have the property that we want, like this one, but we don't know if, I mean, this is one possible choice. There may be other choices. Okay, so one last remark here is that even though we don't know the functions u epsilons, the functions eta we do know. We don't know explicitly what the solutions are. They're not super good looking, but that's what they are. And in the particular case, beta equal to 0, you can choose that one, for instance. That's also rho equal to 1. I didn't write it there, but so these are explicitly characterized, and in the inequality, you can replace everything in the measure that I put there by things that I wrote here. In fact, once you know that the function is a solution to the equation that I wrote before, in dimension 1, sorry, did I say dimension 2? Oh, because everything explicit. Your u epsilons are explicit. The u epsilons here, that my first step is to show that they converge to something. In dimension 2, these are known what they are, so you can compute exactly the limit because you know the function. And the limit is also known because everything is explicit in terms of epsilon, in terms of the parameters, say. So what I wrote in the equation here about the integral, the integral this kappa beta actually is not part of the proof. It's just because we know the functions and we can compute that, and that shows up as a constant in the inequality. So once you know that they solve the equation, you have the integral kind of for free because you know the equations. Okay, so I don't know if you have any questions now, because now I'm going to try to give some ideas about the proof. Yeah. No, not necessarily, because I think in the non-symmetric region, you may have uniqueness of things that are non-symmetric. Yeah, of course, yeah. Yeah. Okay. But yeah, I don't know. In general, I don't know if for some choices of parameters you may have uniqueness. I don't know. I mean, I think in symmetry region, probably you have uniqueness. You have uniqueness in a unique radial solution, let's say. But in the other regions, I think you don't necessarily. Actually, it also depends what you mean by uniqueness, right? Because if you're talking just about the equation, these radially symmetric functions that I show you in dimension 2, sorry, they're solutions sometimes. Solutions are not extremals, right? Yeah, exactly. In that one, those rotationally symmetric solutions in some ranges are still solutions, just not minimizers. So yeah, it depends what you mean by uniqueness. Yeah. Okay, so as I said, there are 3 parts on this. Try to talk about why this converges, and this is a more technical part, so it's the one that I'm gonna give less details, but if you're interested, I can give you more details later. How do we know how the limiting function behaves, or so why does it solve that equation? And how do you get the inequality? The third step, actually, we're reproducing exactly the work of Jean Dolbeau, Maria Esteban, and Tarantello, I think, but with the caveat that we cannot compute explicitly some of the things. So you get an idea there what they did exactly. Okay, so the first thing is that the solution satisfies an equation of this form, that C can be computed explicitly in terms of the optimal constant. And this is the operator that you get, not so good looking, but we're gonna actually do a normalization. So we're gonna take the u epsilons with some constant that maybe I shouldn't call k, but let's say u epsilon or epsilon x, something like that. in a way that actually the equation that we're going to have is this one. You can always do that by choosing the k and the r in a good way. So our equation, maybe I'm gonna, I don't know what I did with the here. Maybe I'm just gonna write the equation for you to have it in mind here. So the equation is gonna be, so here, okay, let me say, L epsilon of u epsilon, gonna be 1 over p epsilon, u epsilon to the p minus 1. This is not very precise, but p epsilon, and I'm gonna normalize also the max of this to be 1 on the unit ball. So here is really the unit interval, so maybe I should just write this. Right. I should write this, and the L epsilon, in case you want to look at it later, is gonna be the principal value of the integral of ux minus uy x minus y. Here, n is 1 for today, so it's going to be 1 plus 2 gamma, x to the alpha, y to the alpha, ex dy. This is the general one, but today we're doing just one. And, okay, so the first thing is talk a little bit about the convergence of this up to this normalization. To have really convergence, you need to normalize in some way. Of course, you can always scale the inequality, and you can get more or less whatever you want here. And in that case, you're not going to have necessarily this type of convergence. So the normalization is important. And there were two things that were known here that we're using. Well, actually, there's one that we're using, and the other one is more like an inspiration. That is the fact that this is decreasing, this first quantity there, u epsilon over x alpha epsilon. So this normalization basically gives you a uniform bound on the function, right? Because you have a bound on the unit interval, and outside is decreasing, so then everything is maximized here. It's just 1, or 1 times some power. And the other thing is that these are actually Helder continuous. This was always studied kind of in particular cases, but it's not so hard to understand that you can actually do it for any parameters where you have symmetry. The problem that we had is that sigma was kind of not explicit, and we need something uniform. So actually, what we needed to do in this step, or the way we approach this step, is try to show that this sigma epsilon can be chosen uniformly. So the main technical part here is to choose the sigma uniformly, and this is actually kind of technical, and I don't want to bore you too much with the details, but I want to tell you what the constant depends on. So the theorem is the following. Even that I had to cut a little bit, and still I missed like some part of the bottom part. But basically, the abstract part is this. As I said before, the uniform norm here we have, because it's the way we normalize. The f is going to be u to some power, so we also have a bound on this because we have a bound on u. And this part is the one that we would be missing here. So this norm is this over here. This I wrote, this is like a weighted L1 norm. And this comes from the fact that the function is an external solution, it's a minimizer. So that bound, actually, you can get, and I'm not going to show you the computation, but basically by comparing with a suitable function, because you can sort of predict what the behavior here is going to be. Okay, so if you choose a good comparison function, this is going to give you exactly the bound on that norm, and this is the step that I'm sort of not doing here, but that can be done. And once you have that, and you can see that all these are uniform. So if gamma is close enough to 1/2, then these are Helder continue with a common exponent. So we have locally uniform convergence, and this is all we need for the next step, that is the inequality. Okay, so Here I put a word about how we do this. It's basically it's a campanato iteration what you're gonna try to set up, which means that you have to do a lot of intermediate kind of annoying steps on how to get bounds for different semi-norms, and eventually you can get what you want by kind of a standard method, but the estimates are not necessarily easy to do. Okay. So let me tell you a little bit more about the characterization of the limit. So as I said before, and I erased, this corresponds to the Dirichlet to Neumann map. In fact, there's a representation formula for that that is exactly this. This you can do just by using the Poisson kernel. And if you recall what the L was, this is just L1 half 0 with some extra constant. That extra constant that appears in the statement of my theorem is exactly this. It's exactly this over here. Okay, so that's that. And why am I writing this? Because then it's not so difficult to see, and we're going to use it at some point, that when epsilon goes to 0, the L epsilon, remember that the alpha was going to 0 and the gamma was going to 1/2. So for a fixed V, it's going to be just the natural limit that you have there, and that's why that appears in the inequality. Okay, so once you have that, the L of u, if you remember that I wrote here, is this here. This is linear, so if you multiply, this is the same as L p epsilon u epsilon, and constant have L equal to 0, so this is the same as the right-hand side over there. And on the other side, this u epsilon to the p minus 1, we can rewrite in that way, just by the definition of eta epsilon that I didn't keep, but I can tell you, if you forgot, eta epsilon was just u epsilon minus 1. The 1 here is a feature of the normalization. I will maybe in a minute say why, but basically if I didn't choose a 1 here, I mean, this is related to this being 1. And showing that this converges actually also tells you, because this is going to infinity, that u epsilon is actually locally uniformly converging to 1. So that's why that's the normalization. So if you choose a different constant here, you can choose a different constant here, and you're going to have constants lying around in different parts. But this is the one that we chose. So the u epsilon, you can write in terms of eta epsilon as it's written there. And because this has good enough convergence properties, and this is not so hard to be convinced about, the L epsilon of eta epsilon is going to converge to L1 half 0 of eta. And the other part is going to be converging to e to the power eta. So this is just kind of the natural limit, and that's where the equation comes from. The normalization is because we get a 1/2 if you want to write it as a Laplacian, and then you can rewrite the equation to get exactly the one that I had before. So it's kind of a choice there. You can just keep the L1/2 0 if you like it better than the fractional Laplacian. And then, as I said before, the value of the integral is something that we can compute explicitly because we know the solutions to that. Okay, so let me go now to the inequality, and let's see. Every time I give this talk, this is kind of the hard part to do because there are many terms to take care of. So let's see if I manage here. Okay, so the first thing is, because this is an extremal solution, we have that inequality. So when you evaluate the quantity in u, then it's smaller than in any other function. Something that I said there, but maybe I didn't write before, is that in the inequality, this long expression that I have, you can also rewrite it in that way. As before, it was gradient square. The equivalent would be here W Laplacian W if we were in the classical case. But you can also write it like this here. So we're going to think about this in this way. Everything here is as smooth as you want, compactly supported. So this is certainly fine for that one. And the way we're going to rewrite the equation now is in this form over here. So I just multiply one way, that over there, and the other one, put it down. So this one, sorry, the one above is this lambda epsilon, and the one below is the kappa epsilon. As I said before, in the classical case, these were explicit quantities. They could compute that explicitly what it was in terms of epsilon. And you could see how this whole thing depended on epsilon. So maybe just like a spoiler in their case, basically you're looking at the first term of the expansion in terms of epsilon of this inequality. The zeroth order term agrees because the way you choose the W epsilon, and then the first term is the inequality that you're looking for, basically. Okay, so basically here we want to do the same thing without knowing exactly what the expansion is, because we don't know the functions explicitly, but we know the limits. Okay, so when you expand the right-hand side, you're going to have something of this form. Then if you recall from the previous one, you were divided by lambda epsilon this quantity. So you're going to have a 1, and the other two quantities divided by lambda epsilon. Okay, so before trying to explain what it is, this is the way that we want to write both of these quantities is maybe like, I'm going to put this down in a second, but basically you want to write this, let's say, I over lambda epsilon. You want to see that this is similar to some limit quantity, so some, let's say, I bar over p epsilon. And then when you take the limit, when epsilon goes to 0, then it's going to be the exponential of this quantity. And that's where the exponentials in the inequality are going to be coming from. So I'm going to show you one of them more or less carefully, and the other ones are similar. Okay, so the first thing is because the u epsilon satisfies that equation over there, and the I1 was something, as you see there, that was u epsilon b L epsilon of u epsilon, then you can replace that L epsilon u epsilon by the equation, and you're going to get that. And lambda epsilon is that quantity for the same reason. Okay, so we already have this 1 over p epsilon that I want to have. So basically what I want to show is that epsilon over lambda epsilon times that is converging to something. So that's what I'm trying to do here. There's an intermediate step that comes again with all these a priori estimates that we had to do before to show actually the convergence. That is that this quantity is uniformly bounded in terms of epsilon. So it doesn't, that bound over there doesn't depend on epsilon. This is a part of the proof that I didn't show you. And that again comes from the fact that this is extremal, and you can find comparison functions that are uniform in epsilon, and that would give you a uniform bound for that. Okay, so having said that, that means that at least up to subsequence, this should be converging to something. So at least that part is going to have a limit. And that tells you that the lambda epsilon, if you take away the p epsilon, that part converges, and you have something divided by p epsilon that we still need to take care of. While the other one, you want to rewrite it in this way. You want to write the power over there as 1 plus eta epsilon over p epsilon, and because you're multiplied by something that's compactly support, the local uniform convergence is going to be enough to tell you that this is converging to v times e to the eta, and below that x to power b, that is the limit that I'm assuming that I already have. Okay, so having said all that, if you collect everything, you know that inside the integral of I1 you're going to have that, that the epsilon, the lambda epsilon times p epsilon is going to be like kappa bar, and then you're going to multiply above and below by p epsilon again. So you have epsilon times p epsilon, and if you want, here you have in the denominator you're going to have, let me write it like this, lambda p epsilon, epsilon, p epsilon. This is the one that I'm assuming is converging to A. This is from the estimate in the previous page, just that integral that is converging to kappa bar. and this is the one that is gonna come with the power that I had before to get the exponential. Okay, so once you have that, you know that at least for this term, what you're gonna get in the limit is something like the exponential of this integral times 2a over kappa bar. For I2, you need to do something similar. I think it's not worth to show all the details because the idea is exactly the same. You want to basically use those relations to make sure that the coefficients are converging properly. And what you're going to see is that the limit of the I2 is going to be this basically half Laplacian that I showed you before. And this last inequality that I'm showing you there is just Fatou's lemma. And the reason why this is there is the original thing that I had, that everything that I've been telling you is about the right-hand side. But the last one that I'm showing you is that this one, the limit is bigger than the limit that we want. So once you run all that approximation there, what you're going to have at the end is this limit. So this is almost exactly what I showed you at the beginning. It's almost inequality that we want, except for one detail, that in my original inequality, the reason why I wanted to compute that integral is because the quantity there was something that I called kappa b, and this k bar is something that is the limit of that integral that I said it has some limit, but I don't know what it is. So the last part of the proof is to show that this kappa bar is exactly kappa b, and basically in the same way that I show you the last inequality there, by Fatou's lemma, you have a comparison. You know that the kappa bar is always bigger than the kappa b. So you need the other inequality. And for that, what you need to show is that actually constants are, you can approximate constants to satisfy this inequality. That you can plug v to be any constant that you want. And once you do that, the first term is going to be 0. There you're going to have some constant, and a to the av is going to be a different constant. But basically, by taking that constant to infinity, you can deduce that the other inequality, that kappa bar is smaller or equal than kappa b. And that's the last part of the proof. And with this, of course, I went too fast because every time that I do slides, I go too fast. And when I don't, I always go too slow. So, well, thank you for your attention. That's a good question. So, okay, so the inequality you have to think about as a boundary inequality. So somehow it's a version of, instead of having the sphere, having a disk with a boundary. So I think you can give a geometric interpretation in that sense. You can write this as an equivalent to the Onofre inequality, but with a boundary. But we haven't really explored that connection yet. It's R, but then by a stereographic projection, you can project it into a disk. Yeah, yeah, yeah. So yeah, I think this is kind of an interesting question that the answer I think is yes, but I cannot tell you exactly what the interpretation is at the moment.